all. So this is the part that you asked John to program up for you. In the main, it appears more to be a 3+2 axis machining routine, but John was able to get some full 5-axis simultaneous stuff to go in there as well. What I'll do is I will go through the principles that he used in order to program this part up and arrive at the finished article. What we have here is we have the surfaces that have been triangulated. The metric triangulation tolerance there, 0.022. And we've got 3 sets of folders here. Now, folder 1 contains all of the bits and pieces that John has used in order to construct the containment boundaries. So there are boundaries that are created at different angles to give us our A and C rotations. I then put everything into 2 separate subfolders for all of the machining itself. So in the first one, we have all the roughing routines. And if we delve into how the item was constructed for machining, I look into the history of this item. So there are all my machining paths for the first face. If I look at the model that he used, I can see that he's made a slight change to the original model. He has prepared this and he has capped over some of the holes that would cause him a problem when he machined from the side. So what he's done is he's taken the original model and created some extra parts to go in and cap the holes over. He's then created a bounding box that is on its side. Normally, normal 3-axis machining, the bounding box comes in from the top. So if I was to create a standard bounding box here, you see there's no rotations. And the bounding box is from the top. Now it's this bounding box, this is what gives it the tool axis normal direction. So to create these passes on the side here, we've had to create a bounding box that is on its side. So in order to get something like this, you need to have the triangulated surfaces folder highlighted. And if you then hold down the N key on the keyboard and click on the surface, it will give you the surface normal. You can then, by holding the control key down and choosing the bounding box function, have various different options. So the second option here is apply the current view rotation. So if we check that, and I click OK, it will then bring up the dialog box for creating a boundary, a containment boundary, and puts in the maximum and minimum limits of this item. Now John has reduced the size of this item. If I click this one, it's going to give me something that covers the entire product. Okay, so you can adjust the numbers. If I go back to the properties there, the size of this part can be adjusted by editing the values here. tidy. So once he has the surfaces that he's going to use, the next option is to create the passes that are going to go onto it. Let me just get some values from here to start with. Okay. So what we would do is we would select the triangulated surfaces. You'd hold the control key down. You would select the bounding box. You would then, from either the passes ribbon menu or from a right mouse click, choose, in this case, adaptive clearance toolpath. This presents the dialog for the toolpath, where we can enter the values for the cutting tool, diameter, corner radius, tapers if required, flute length and body length. Most important is the body length, because this is the length of the cutter out of the chuck. Let me just paste in the parameters that John used for this particular cut, and you'll see that he's also added in a tool holder. If I go onto the holder page here, where's that coming from? So the tool holder is described as a series of diameters and heights. So the first coordinate point is a point at 0, 0, right in the center. Our second coordinate is at 46, 0, out here, and then a point here at 50, 65, and a further point up here at 50, 90. You can make this as elaborate as you want, or as basic as you want, providing, of course, this profile actually gives you clearance over your tool holder. By default, the clearance on the tool holder is 1 millimeter. You can obviously increase or decrease that as you require. If we just go back and look at the tool, there are other pages here. So we have the cutter page, which defines the cutter itself. So flute length, corner radiuses, etc., all dialed in here. There is an advanced page. Here you can set up the tool number, number of teeth, and various other basic parameters, spindle speeds and feeds and coolants. You get an opportunity later on in the process to verify these values, and they can be changed later on if you require. Cutter animation. So we can see here we've got a 3D cutter animation of the tool path itself. The dialog down here can be adjusted for speeds, so we can make this slightly faster if we want to, or you can race through the options backwards and forwards, pause it, rewind it, etc. If you have a realistic and accurate feed rate here, then the estimated time is correct. So if we had a slow feed rate in here, okay, so we're running at 73% of real time, then my estimated time is 19 minutes. If I bring this back up to whatever the programmed feed rate was, 100%, there we go, then you'll see that my estimated time is 14 minutes and 13 seconds. This records the exact position that the cutter is within the toolpath length. So this is now 16 meters 800 into the toolpath. And at the bottom right hand corner we have the X and Y Z coordinates of the tool tip. So that was the first toolpath to rough out this front end. In a similar way, a bounding box was created on its side at a rotation of A90, C minus 90. And so we then cut from this side. And I believe John created, yes, he created one on the other side here. In order to be able to cut and paste values, so all of the values from this adaptive clearance toolpath would be exactly the same as we need to use on the opposite side. So if you do a right mouse click in the dialog, you can then have the opportunity to copy the parameters. So in this case, if I was to copy all of the pages, it's going to copy everything: tool, cutter, advanced pages, the passes, the linking, etc. So once we have the edited the surfaces that we're going to machine, hold the control key and select the bounding box, right mouse click, adaptive clearance toolpath again. Now I can right mouse click and I can paste the parameters, and that will populate all of these pages to exactly the same as they were on the one I copied them from. So using 3+2 machining is by far the most rigid way to rough a part out for 5-axis machining. So 3 sides and the back now 4 sides, all using adaptive clearance toolpaths, which is a trochoidal style machining routine. A little bit of extra work to do on this fillet radius at the back here. And then finally, an adaptive clearance toolpath to finish the work off on the top of the component. If you select all of these items and do a right mouse click, you can then create a stock model of those toolpaths to get a visualization of what material has been removed. There is a calculation time incorporated in that, so I'm going to use the model that John used to start with. And if I can just, there we go. Let me switch this off. Okay. So after those 6 toolpaths have been executed, this is what we should have on the machine. So further roughing. The front face, if we look at this, the front face, as you'll see, is stepped. So a toolpath has gone in here now in order to machine the front face, to flatten it down. It goes around the outside of the perimeter and then comes back in. do the inside parts. Bottoms of the pockets in a similar way. Horizontal area toolpath, so this will only look at machining flat planar areas. Yeah, excuse me 1 minute, gentlemen. 1 second. Okay, sorry about that. Okay, so we're still nibbling material out. The numbers on the end of this line denote the cutter size, so a 16x0 cutter, and this has a common thickness in X, Y, and Z of 0.25. So all of the machining that's gone on here has got a common thickness X, Y, and Z of plus 0.25. So if we make a comparison between the stock models of the first set of 6 tool paths and then with the additional 3 that's in here, we can see where the additional material has been taken off. Now some work on these thin wall bosses. So work on the left hand side and an adaptive clearance toolpath to get into the boss. So we're now starting to use the complete model again, not the one that's been had the planar patches put on the end caps. So the left side and again the right side, exactly the same. We're using the edited silhouette boundaries, so we're just working within this silhouette boundary, the containment boundary, so no machining outside of that. And working on doing the rest of the holes. So everything, as we work down through here, everything has got plus stock material of 0.25. And finally, if we look at that, so after the roughing process, this is what we have achieved. Now the next stage for you guys is you need to take these internal toolpaths and you then need to process them. Because you're going to go through the testing stages, then you will be doing these one at a time. The next process here is that we need to verify the cutting parameters. So all of these toolpaths that we're presenting have the passes created and those passes have been linked. So in order to verify the parameters, select the toolpath and do a right mouse click. From the right mouse click context menu, the drop down, you can choose cutting parameters. The other place that you will be able to go to do that will be on the toolpath ribbon menu, and for whichever item you have selected, you will be able to achieve the option to get to the cutting parameters here. So this predominantly verifies what we had in the advanced page. Okay, so this is a verification. This just checks these values here, and you can overwrite the tool number if you wish. At this point, we can change that. We can upgrade the spindle speeds. We can put in datum offsets as well if we require. We can alter the coolant condition, and we can modify the feed rates. You'll notice that the icon has changed on the side here. So we've now gone from the adaptive clearance toolpath machining icon. We now have the parameters verified and set. And the final part of the process is we need to post-process. You must just excuse me for one moment because I need to make a change to my system options, because I need to use GPost, and we need this VM10. So now when I right mouse click and say post process, the format is set up for the post process that Sam has sent to you, and the directory that it's going to create the file in is the system directory where your part originally resided in your file system, unless you make changes because you want to direct it somewhere else. Clicking OK will execute the toolpath post processor. Just wait a few seconds for this to conclude. Okay, close that down. If I do a right mouse click on here, I then have the options to do various things with this this file. So let's go and have a look and see what the data is. So hopefully this should look fairly familiar to you guys. So starting the process up, information about various M codes and G codes, and then the data itself. So you need to do this for each of these toolpaths as you are going to work through it. So be a right mouse click, cutting parameters, verify the tool that you're using, tool number particularly, right mouse, post process. So once you have the post processor file created, you can then either create a tool sheet of each individual post processed folder, or you could select a group of them, right mouse click and create a tool sheet. This will create an XML file, and if we view that, then this will give you information about your project. You get a view of the part that's being machined, information about database names and prefix names, total physical part size, and then the motion limits of the toolpaths that have been included in this group and what those toolpaths are. Current estimated machining time for the two toolpaths we've selected is 52 minutes, and you get information about the cutter that's being used and then each and every toolpath that was selected. Masses of information down here to help the setter set the machine up. Everything that he should require is there. So that was the roughing routines. There's an awful lot more toolpaths for the finishing routines, and I'm not going to go through all of them. I think you can understand the principles that are being used. If you've gone through the training manuals, then you will know how to use all of the 3-axis routines. So they incorporate the horizontal area, toolpath, water lines, boundaries. You can have rasters. We've got helical toolpaths. We've got a whole group of things there. Each of those is going on a different surface or a different group of elements or at different angles in order to finish machine this part. So what you would notice in this tree here is that the end value is now always 0. There's a few extra passes going on here with the swarf machining because this is a 5-axis routine, so there's a certain amount of semi-finishing going on in this process. And what we'll do is, I'm not going to dwell on the 3-axis stuff, but we will look at some of the 5-axis machining. So if I briefly animate this toolpath, try and get this into a position where you can see what's going on. So you'll see that that tool is rising and falling and is using the flute of the cutter in order to machine this straight edged set of surfaces. Okay, it rises and falls down that edge as well. So the process to be able to get at this group of surfaces here for swarf machining requires some additional separation of surfaces and the creation of some curves. So what is required is we need to separate out the surfaces that we're going to actually machine, and we need to separate out some surfaces that we want to avoid. So the surfaces that we want to avoid are surfaces at the top and surfaces at the bottom connecting with the drive surfaces. So in order to do that, in order to create these groups, we take the triangulated surface folder, make sure that it is highlighted, select the first surface, hold the control key down, select the remaining surfaces. Right mouse click, come down to label geometry. Now label geometry will take the selected surfaces and put them into a new triangulated surface list. It will be called triangulated surfaces. If we want to define it slightly better, if I hold the control key down when I say label geometry, it will put it into a folder that has the word drive in front of it. Switch that off. So this now is my set of drive surfaces, and I do exactly the same thing if I'm trying to select surfaces that I want to have as check surfaces. So if I select that top surface, hold the control key and selected these ones around the side here as my check surfaces and did a right mouse click, label geometry. This time though, don't hold the control key down, hold the shift key down. Shift key, label geometry, and that will then create a separate folder, but this time it has the word check in front of it. It's just so that we know what's what. Okay. The next thing we need is some curves to go around that geometry in order to guide the bottom of the cutter. Okay. You can only have, in this case, one folder, and within that folder you can have an item which is on its own. So to achieve that, take the drive surfaces for sure, because it's going to be the curve that runs around either the bottom or the top or an edge like that. Come to the curves ribbon menu and extract the converted curves. Now at this moment in time, do not join the curves. We need to do some editing on this to remove some elements, but it's going to create curves of all of these pieces. So to start with, don't join. If I look into the folder here now for my curves tessellations, you'll see I have many curves in there. For each of the panels, you will have a curve at the top and a group of curves at the bottom. You will also get two curves where any two panels join together. Okay. So in this instance, what I need is, if I select all of those items, so that's the top curves and the 8 elements that make the legs, select them, delete them. Check my list and you'll see I've got various different items in here now. Now I can take that list, join the curves, and my bitangency angle needs to be fairly steep to make sure that I actually make connections between sharp corners. So we'll just increase this to 170 in this instance. And if we then do a final check on that, you'll see that I've got one curve that follows the bottom of the check, the drive surfaces. Okay, just going to shortcut this process a second. So the next important thing is the ordering. So you select the drive surfaces, you select the curves that you're going to follow, you select the check surfaces, and from either the 5-axis ribbon menu or from a right mouse click, you will get to your 5-axis machining options. In this case, we're using swarf machining because we're using the flute of the cutter to form the side wall of that component. There is the 5-axis swarf machining dialog, and you either create your tool in here to your specification, or you can load a tool from a library, or you can copy and paste from other dialogues in the system in order to create your tool. So the toolpath created by the swarf machining. Goes around the outside edge of that. We've also got similar swarf machining, taking some extra material off. So the first one went round with a 0.1 thickness on X and Y with a 0 on Z, and then the second one goes around and takes a spring cut around there in order to remove the final amount of material. Nibbling away at some of the flat areas underneath. And then some more 5-axis machining here. So the front of the circular pockets. So swarf machining on that with some stock material on to semi-finish it. And the D-shaped pocket on the other side, same process. Okay, some work on this top edge now. So again, you'll see the surfaces have been segregated. So we have a group that create the drive surface. And we have another group that creates the check surfaces. So ones we want to avoid. And then in this case with the swarf machining, it looks like there are 2 sets of curves. Okay, right, 2 sets of curves in this instance. What the second set of curves does is you'll notice that the first set should follow the end of the drive surface data. And the second set of curves actually controls the tool axis. So if I animate this toolpath for you, keep it fairly slow. So when we start cutting, you'll see that the tool axis is in line with this curve here. And then gradually, as we move around the part, okay, so we're still in line at this point, and then we start to crank the tool up and over as we roll around this top edge. Okay. As you come over the center line, you should be almost vertical. See if I can get that centralized. And then you pick up the angle for the next curve that's given the direction for the tool axis. And then as we come around the far side, we're back in line again. The system knows how to handle the number of files that are presented to it. So it's always looking to have a drive surface presented to it. It's always looking to have a check surface. It will always want at least 1 set of curves to drive on. If you give additional curves, it assumes that these are guide curves for the tool axis control. First pass and second pass. Extra bits and pieces in there. Okay, some tricky undercuts in order to get these chamfers on the back. And what's happened here is we have selected the chamfer surfaces and done UV or created UV toolpaths on them. So we've selected those 2 surfaces. And also there should be a silhouette boundary to give it a direction. So we've sorted out the silhouette boundary at an angle in order to give us the tool axis that we need. We've then selected these surfaces, and from the usual passes page, we've then created a UV surface set. Now that UV surface set puts directions onto the surface data. So we have a flow direction, which is the yellow arrow direction. And we have a step over direction, which is defined by the green arrow. So we're starting off at the inside and stepping out towards the outside. In this case, it's just two surfaces. They happen to fall nicely so that everything is a common direction. Sometimes they're not in the right directions, but you can make modifications by swapping the cut and the order directions and reversing the UVs on the other two as well.
Hey, hi, Dennis.
Yep.
Yeah, I was thinking about this this part, right? I think we can just skip it. There's no need to do this. I'm thinking. What do you think? I mean, I mean, it's not a customer part itself. It's just a demo part. So I'm thinking that the key thing is to really showcase the multiple site machining. That at the same time the simultaneous movement, that it's more towards the tapered corner. So I'm thinking this one we can just do a hole and that's it. Yeah.
Okay. Right.
Yeah, I'm thinking there's no need to be too stressed over that. Yeah.
Right. Yeah. I mean, I'm pretty much got to the end of sort of showing you what's what. Because have you got this file at the moment? Has John given you this yet?
No, we have not got this file yet. Yeah.
Okay. Right. Yeah. So I can either send you the file that I have here, so that you can then carry on and do the machining routines that are required.
Okay. Sounds good. Yeah.
Yeah.
Because what we intend to do is once we get the files, we'll get the cutters and everything else, and the machine is just at our showroom now in Singapore. So we will do the test cut in Singapore, and then we do likewise in Taiwan as well. So so that at least we have enough time before the actual workshop session in Taiwan.
Yes. Okay. Right. Yeah. So I think that's everything that I need to go through. So we've seen the roughing and the finishing routines. I presume sort of through the training that you've done, sort of particularly with the 3-axis stuff, you'll be familiar with all of this stuff. You know, the 3-axis is easy. 5-axis is a bit more complicated, but not too difficult. And yeah, the UV stuff that we've shown, that's sort of all of these ones with these markings on it are predominantly 3-axis or 3+2, and then we've got the 5-axis add-on stuff as well. So yeah, if you're happy with that, then guys, I think best thing for me to do is to put this file up onto the FTP site, and then you can get it from there.
Okay, sounds good.
Yeah.
Yep.
Okay, excellent. Well, good to talk to you guys this morning. I hope that's been useful, and we can get together again as this progresses, and the closer you get to the show, and sort of fine-tune things for you.
Sounds good. Sounds good. So, yep, once we get the files, we'll take a look at it and, you know, do the simulation on the machine itself, and let's see whether there are any issues that we foresee. Yep.
Sure thing.
Okay.
Okay, I will upload this to the FTP site directly after this meeting, so it should be there in the next 10 minutes.
Perfect. Yeah. 明天我们有那 FTP 上的东西啊，有吗 ？FTP 的资料，好，有啊。OK。
Yeah.
Okay, sounds good, Dennis.
Okay, excellent.
Thanks for your time.
Take care. Have a
Yep.
good day. Well, it's
Same
end
to
of
you.
the day
Take
here,
care.
isn't it? Yep. Okay.
Bye-bye.
Cheers for now. Bye.